All right, here we are with our last video here for Chapter 6. We're looking at geometric settings. So we just spent the last two videos talking about binomial settings and binomial distributions and their probabilities. And we're going to talk just briefly here about geometric settings. They're very similar to binomial probabilities, but just a little bit different. It says in a binomial setting, the number of trials n is fixed, and the binomial random variable is the number of successes in those n trials. In other words, the goal was to repeat the chance behavior until success occurs. If this happens, however, this is referred to as a geometric setting. So again, binomial fixed number of observations. In geometric, we're going to go until we get that first success. All the other conditions are the same. And by that we mean that we have to have either a success or a failure. We have to have independent trials. And the probability of success remains the same for each. Now, it says that if in a geometric setting we define the random variable y, again, could be any letter we want there, as the number of trials needed for the first success, then y is called a geometric random variable. And the probability of y is called the geometric distribution. So we say here the number of trials y that it takes to get a success in a geometric setting is the geometric random variable. The vocabulary all kind of sound similar, but when we talk about each part, we have to be clear on what it is that we're referencing. So the probability distribution of y is a geometric distribution with parameter p. So when we identify the geometric random variable, all we have to talk about is the p, the probability of success, as opposed to binomial distribution when we had to identify the n and the p, or a normal distribution when we had to identify the mean and the standard deviation. Here with geometrics, all we have to do is identify p, because that's all we need to know to find the probabilities. And it says the probability of success on any trial, that's the p. And the possible values are 1, 2, 3, etc. Now, that's a little bit different than binomial distribution as well, because it was possible to have an x value, if x were a binomial random variable, to be 0, because we have 0 successes out of the n trials. But you can't have your first success on the 0th trial. It doesn't make any sense here. You have to have it at least on the first trial. And it says on the bottom, like binomial random variables, it's important to be able to distinguish situations in which geometric distribution does and does not apply. So let's look at an example. This is called the lucky day game, and we're going to be spending more time on this in class, but just an introduction here. It says the random variable interest in this game is y, the number of guesses it takes to correctly match the lucky day. What's the probability of success of the first student guesses correctly, the second, the third? What's the probability that the kth student guesses correctly? Now, if we think about this here, is this a geometric distribution? Well, yes, it is, because we're going to guess until someone correctly matches the lucky day. So if the first person guesses correctly the lucky day, then they're done. But if the second person is the first person to correctly guess the second day, then that would be done. So that's the difference between x equals 1, or excuse me, y equals 1 or y equals 2. When we look down here, we say the probability that y equals 1 is 1/7 because there are 7 days. And obviously, if you're just guessing randomly, the probability of success on the first trial is 1/7. But if we have y equals 2, that means the first student guessed incorrectly. So that's 6/7 as a probability. And the probability that the second child guesses correctly is 1/7. So to find the probability that y equals 2, we just multiply 6/7 times 1/7, and we get about 0.1224. And we can continue with y equals 3. That would be the first two guessed incorrectly and the third guessed correctly. Probability of about 0.1050. And we could continue on with that, or we could generalize the formula as we see in the bottom here. The probability that y equals k, in other words, that the first success happens on the kth trial. To find that probability, all you do is 1 minus p to the k minus 1 times p. Now, if you break that down, you know p is the probability of success. So 1 minus p, therefore, has to be the probability of failure. And the reason that we raise the probability of failure to the k minus 1 is because every observation other than the last one was a failure. So that's why we do k minus 1 as the exponent for the probability of failure. And then we just multiply it by the last observation being a success, p. Now, a couple things to note about when we look at these distributions. When we looked at the binomial random variable, the shape of that distribution varied depending on what p was. But when we look at the shape of the geometric random variable, it's always going to be skewed to the right. Because if you think about it, when you go from the probability that x equals, or in this case y, probability that y equals 1 to y equals 2, you're multiplying by the probability of failure each time. You go from 1 to 2 or 2 to 3 or 3 to 4, etc. And that's obviously between 0 and 1. So the probability is always going to be going down. So the highest probability is when y equals 1, whether you look at the chart or the graph on the left here. So the shape is always going to be skewed to the right. That can't change regardless of the probability of success. We noted that when we had the binomial distribution, we could change or alter that shape based on what the p value was and also how large the sample size was as well. As far as the center, well, we could find the mean of this distribution as 7. And the reason that we get that is because the probability of success is going to be 1 out of 7. So 1 out of every 7 we expect to get correct, so the mean is going to be 7. A more simple way to identify that is the expected value of y, or mu sub y, is just 1 over p. So since we have 1 over 1/7, that reduces to just 7. That would be our center here. And as far as the standard deviation of y, well, we could just go ahead and use the rule for the discrete random variable to go along with this here. You won't be asked to find the standard deviation for these geometric random variables, but you will be asked to find the mean of these here. And that's it for this chapter. If you take a look at these objectives, these are the things that we really focus on. We started off talking about whether a distribution was binomial or not. We found the probabilities for binomial distributions. We found the mean and standard deviation for binomial distributions, and we also interpreted what those values meant. And this video here, we talked about whether a random variable was geometric or not, and we found probabilities associated with that. And even though it's not an AP topic, we did talk about how you can use normal approximation for binomial distributions as well. So that's it. We're going to spend some time in class reviewing some problems as well, and we'll be having our test coming up pretty soon. Good luck.